Hey everybody, in this video I will be covering the examples for the Unit 1 for response question packet that I created. All these problems, I've only included parts to the problem that had to do with limits or continuity, anything from the first unit in the curriculum. I've selected 4 problems here. This first one. The original problem gives us a differential equation. A differential equation is any equation that has x's and y's mixed up, and you will see a dy dx somewhere in there, or a y prime somewhere in there. That's a differential equation. What you'll notice in most of these problems is that they incorporate some contextual knowledge, meaning it's not strictly from Unit 1. It may be Unit 1 mixed with something else. So this first problem is Unit 1 limits mixed with a differential equation. So you have to have knowledge of different areas and know how to connect those two things together. So in this first part of problem 5 from 2013, it asks us to find this limit. And we have some information up here. So the first thing I'm going to put here is kind of what I know about dy dx. It's also the slope, or the first derivative, or in other words, f prime of x. And we also know some more information. We also know that f of 0 is equal to negative 1. Now, in this first problem, when we're solving this limit, we have to, our first step is always to try to plug in a 0. So if I just think to myself in my head, if I plug in a 0 in for f of x, f of 0 is negative 1. Negative 1 plus 1 is 0. So I know the numerator is 0. When I plug in this value here. When I plug in 0 to the denominator, sine of 0 is also 0. So I get a 0 over 0, indeterminate form. This is a L'Hopital's rule problem. But before I just do L'Hopital's rule, I have to show that I know why I'm using it. And the way they want you to write your work on the AP test, if it is a L'Hopital's problem, is you need to write your numerator and denominator separately at first. So over off to the side, I'm first going to write numerator, or this is just to kind of organize the work so you see what I'm doing. For the numerator, I have to show that the limit for just that stuff, f of x plus 1, is equal to 0. So this is equal to f of 0 plus 1, which is equal to negative 1 plus 1, which is equal to 0. Now I have to show the denominator separately. So I'll just abbreviate that there. That the limit as x approaches 0 of the denominator sine of x is equal to sine of 0, which is equal to 0. Okay, so once I've shown these two things, now I can use L'Hopital's rule. So over off to the side now here, I'm going to put by L'Hopital's rule, I'm going to rewrite the original limit again. That's my starting point. The limit as f of x plus 1 over sine of x. So now by L'Hopital's rule, I've showed this already, 0 over 0. Now what I need to do is I need to set this equal to, and I can now start taking the derivatives of the numerator and the denominator. So I know by L'Hopital's rule now that the limit of x as x approaches 0 of, now I take the first derivative of the numerator, which is f prime of x. The derivative of plus 1 is just 0. The derivative of sine is going to be cosine. And so this will be equal to f prime of 0 over cosine of 0. So here I'm going to write f prime of 0 over cosine of 0 because I know these two things are defined. And all I need to do is evaluate each of these. So first off, I know what cosine of 0 is. It's 1. Cosine of 0 is 1. And then now I need to figure out what is f prime of 0. Well, f prime we wrote at the very beginning is right here. And I can plug in a 0 here for x. But now you might be thinking, why is there this y squared here? What do I need to do? if it's a differential equation, you'll need to plug in the x and the y value for that coordinate. So the xy coordinate is right here. It gives it to us. It's 0, negative 1. So if I'm plugging in a 0 for x, I need to plug in a negative 1 for the y. So this ends up being 2 times 0 plus 2, which is 2, and negative 1 squared, which is positive 1. So this ends up being positive 1 times 2, or just 2. So my answer here is just 2 over 1, or just 2. And that's our final answer here. Let's move on to the next problem. This was from last year, 2019, the AB version of the test, number 6. It gives us some information. This one is part D. The reason that part D is part of Unit 1 is because if you look on your study guide, I mentioned that anytime you see a problem with this type of an inequality, this is indicating to me that I need to use the squeeze theorem. Okay, this is a red flag to me, or an indicator, immediate signal that squeeze theorem is going to be used here, because I see these three functions in an inequality. The initial problem tells us some information. It tells us that g of 2 is equal to h of 2 is equal to 4. They're all equal to 4. And it also tells us this tangent line right here. We may or may not need that for part D. Okay, part D says it is known that g is less than 8 or equal to h. And up here, I see g and h, and it matches, it tells us what's going on with g and h. Let k be a function, so I don't see a k up here. K is a new function that it's introducing, the problem is introducing. Let k be a function satisfying that it's in between g and h. So we know g is always less than h, and now this problem is telling us k is in between them, in this interval from 1 to 3. So if you were to kind of visualize this on a graph, oops, sorry, it's not very perfect, but all right, 1 to 3. So it's telling me that g is always below h. So g I'll draw down here, and h is somewhere up there. I just drew that arbitrarily though, but I didn't meet the requirements for it, because look at what it tells us at the beginning of the problem. G of 2 and h of 2 are equal to 4. So I'm going to erase that, what I just drew, and at 2, both of those functions are equal to 4. So I know that g has to touch the 4, but it also has to stay below h, like that. But they both have to be equal to 4 at this point right here. So this is kind of what this graph might look like. I'm still meeting this inequality right here, g is less than h, and they both meet up at 4. I'm still meeting those requirements. Now it's asking us if k is less than h but greater than g, meaning it's in between them, does k have to be continuous? At x equals 2, we have to justify our answer. So now using squeeze theorem, we can justify if k is continuous or not. So the first thing that we need to show is that g and h are continuous. Okay, I know I already drew that here, but I need to draw why it's, or I need to explain why it's continuous, and that's kind of written up here. This word differentiable, that automatically includes continuity. If something is differentiable, that means you can find the slope at any point, which means that all the points already have to be defined. So differentiable already includes being continuous. They don't mean the same thing. They just mean that if a function is differentiable, it must also be continuous. It must also have a point at every defined at every single point. So the first thing I need to show here is that g and h are continuous at x equals 2 because they are differentiable. Okay, so now we've showed that G and H are continuous. And now connecting that with this idea right here, that the point at 4, at the point at the x value 2 is equal to 4, now I can also say that therefore the limit as x approaches 2 of g of x is equal to the limit as x approaches 2 for h of x. Both of those limits also have to equal each other because they're both approaching the same value and they both are equal to the same value. Okay, so they're both continuous, and so they both have to have their limits be the same as well at that point. When x is approaching 2, they both touch that value 4 and are defined there as well. So I know all of this information right here. So now what does this have to do with the function k? So now the problem tells us that if these two guys have the same limit and k is in between there, the squeeze theorem tells me that if the two outside guys have the same limit, then the inside guy must have the same limit as well. So I'm going to put, for my second point, since g is less than k is less than h, then the limit as x approaches 2 of k of x must also equal 4. Okay? The squeeze theorem tells me that all of the limits have to be equal to the same thing if this holds true right here. And then we also have that since g of 2 and h of 2 up here, g of 2 and h of 2 are equal to 4, it must also follow by this inequality less than or equal to less than or equal to that k must also be equal to 4. So I'm going to extend this sentence and say and k of 2 equals 4. Therefore now, so now we've showed that if k of 2 equals 4 and the limit is equal to 4, those two things are equal to the same thing. This is the definition of continuity. Okay, you can refer to your study guide to see the steps for a definition of continuity, but it's right here. The limit and the limit is equal to the point defined there. So therefore, I'm going to say k is continuous. All right, and there's the squeeze theorem. And go on to the next page. This is 2010, number 5. This is similar to the first problem we just worked. It has a differential equation here, and it also has a limit. We're not going to work part A. That's not supposed to be here. It's Euler's method. It's part of a different unit, so we'll work on it in a different video. But this is going to be just for part B. So here I have some information. I have the differential equation here. This is also, in other words, f prime of x, the first derivative. And then I'm also going to highlight this other point that we know right here. F of 1 is equal to 0. Okay, that will help us in our problem here. So now before I even start writing anything, let me just think about what's going to happen here and see if it's going to be L'Hopital's. So x is approaching 1. F of 1 is 0. Okay, so we have 0 in the numerator. And then 1 cubed minus 1 is also 0. This is going to be a L'Hopital's rule. So I'll do this one a little bit faster. But for the numerator, the limit we just said will be equal to 0. F of 0 equals, sorry, f of 1 equals 0. And then we have the denominator. The limit as x approaches 1 for x cubed minus 1 is equal to 1 cubed minus 1, which is equal to 0. Okay. I know this is a lot of writing here, but I would rather put all of my work because it tells me show the work that leads to your answer. I don't want to leave anything off that would give the grader a reason to deduct points. I want to be as thorough as possible, but at the same time, I don't want to lose too much time. Okay, but writing this calculation or this step down right here doesn't take much extra time. It just shows that I know what I'm doing. Okay, I've shown the 0 over 0 indeterminate form. Now I can start using L'Hopital's rule. So I'm going to say by L'Hopital's rule, I have that the limit, the original one, approaching x is approaching 1. I've got f of x over x cubed minus 1. Now I can write the next limit as x approaches 1 for the derivatives here. So the limit x approaches 1, f prime of x over 3x squared, the derivative of the denominator. So f prime of 1 over 3 times 1 squared is just 3. So I'll put 3 in the denominator. And if I look at f prime of 1, that means I need to plug a 1 into this function right here. Well, this is a little confusing because I just have 1 minus y. So we talked about in the previous problem, if it's a differential equation, you'll have to plug both the x and the y into your equation. So here there's nowhere to plug in the x value 1. So we don't need to plug in a 1 anywhere because there's nowhere to plug it into. We do have a space to plug in y though, which is 0. 1 minus 0 is going to be a 1 over here. So my limit is approaching 1/3. So don't get confused there. You want to make sure you plug in the correct coordinate into the correct variable. Last question here. This is part D from 2018, number 5. Gives us this function e to the x times cosine of x. And it tells us let g be a differentiable function such that g of pi over 2 is equal to 0. So that's important. We'll use that. And the graph of g prime is shown down here. So we know one coordinate on the original function, and we know what the derivative graph looks like. So I'm going to make a note of this down here. It's g prime, not g, so don't let that confuse you. It's the derivative. This is kind of guiding us and telling us, hey, use L'Hopital's rule, because we got a 0 right here and we have a derivative right there. Those are two things we kind of need for L'Hopital's. And so the limit as x approaches pi over 2 of f of x, I'm showing the numerator is equal to 0 because cosine of pi over 2 is 0 times e to the pi over 2 is still 0. So this is equal to e to the pi over 2 times cosine pi over 2. Whoops. That's equal to 0. That's the numerator. And now the denominator, we're going to do the same thing. We don't know the function for g, but we do know that coordinate. G, we just write g of pi over 2 is equal to 0. It tells us that right here. We know that. So now I can use L'Hopital's. It's important that you write the word L'Hopital's in there after you notice that you're supposed to use it. By L'Hopital's rule, now you can start that process of taking the derivative. So we're going to put f of x over g of x. Don't just jump straight to the derivatives. Make sure you write the original limit first because you're showing that you know that L'Hopital's rule means that the original functions, numerator and denominator, that limit is equal to the same limit of the derivatives in the numerator and denominator. So the key point here is make sure you still write this guy in, and then you write equals, and then in your next step you start deriving. The limit as x approaches pi by 2 of f prime of x over g prime of x is equal to. So to find f prime of x, what we can do here is take this derivative of e to the x cosine of x, I'm not going to show that work here. You can just do the product rule, derivative of the first times the second, plus derivative of the second times the first. When you do that, though, you will get e to the pi over 2. Let me just confirm and make sure that's correct. Sorry, negative e to the pi over 2. All over g prime of x. So g prime of pi over 2. So I go over here to the graph at pi over 2. G prime of pi over 2 is at the value 2. So I'm going to put divided by 2 here. Okay, and there's your final answer. You can leave your answer in terms of e and pi. You don't need to write down the decimal value, even though you have a calculator. I would suggest leaving it like this. The problems on the AP test are going to be designed so that you don't necessarily need a calculator. These problems that are going to be on the AP test this year don't require you to have a calculator. You can have it with you if you have access to one, but you don't have to have one. These problems are written in such a way that they can be done without calculator. It's more focusing on, can you use calculus to solve the problem, not your calculator. So any answer, you can leave it in terms of e and pi. You don't need to simplify it any further once it's a numerical expression. If there's no variables left in it, you can leave it as is, and they will accept that for full credit, even though it's unsimplified. That goes for any free response problem.